Welcome everyone. In the previous video, we have introduced the application for the Schottky diode as a detector. Now we are going to represent uh, how this detector can be used to build up what is called a spectrum analyzer. The spectrum analyzer is a device which introduces the frequency domain representation of the signal. Uh, in this equipment, the output is displaying the average power density versus the frequency. If we compare the spectrum analyzer to the oscilloscope, we can say that the function of the spectrum analyzer is a dual for the oscilloscope. The oscilloscope is displaying the average power or the amplitude of the signal, not the power, the amplitude of the voltage signal as a function of time. But here, the spectrum analyzer is displaying the power as a function of the frequency. So we can say that the spectrum analyzer is displaying the signal in frequency domain, while the oscilloscope is displaying the signal in time domain. Or in other words, the spectrum analyzer represents the Fourier transform of the signal. The spectrum analyzer is basically a sensitive receiver that tunes over specified frequency band and give video output that's proportional to the signal output power or the signal power at this narrow bandwidth. The spectrum analyzer or conventional spectrum analyzer introduces the amplitude of the power as a function of the frequency, but it doesn't introduce what is the phase of the signal. More recently, we have something called signal analyzer. The difference between signal analyzer and spectrum analyzer measure the amplitude of the frequency component as a function of the frequency. But the signal analyzer calculates the amplitude of the signal and the phase of the signal. So spectrum analyzer is mainly based on detecting the amplitude. That's why our discussion here in spectrum analyzer is related to the Schottky diode as a detector, because the detector detects the amplitude of the signal. It doesn't detect the phase of the signal. Spectrum analyzers are used for measuring the modulation products, the harmonics, the intermodulation distortion, the noise level, and the interference effect. So assume that any problem in your mind, and you say that, okay, this is a signal as a function of the frequency, we can measure it by using the spectrum analyzer. For example, in the case of modulation signal, we have the carrier and the sidebands of the carrier. What is the amplitude of the sideband with respect to the carrier? This can be measured by the spectrum analyzer. For the case of an amplifier, for example, and we are interested in determining its dynamic range, so we are going to change the input power, and we will see the output power, and we will see when the output power is below the noise level, so we have some noise level, and when the power is slightly greater than the noise level, and by measuring the amplitude of the power as a function of the input power, when the relation would be nonlinear, or we can determine what is called 1 dB compression, and so on. So effectively, any problem which can be described in a frequency domain, it can be measured by using a conventional spectrum analyzer. The block diagram of a conventional spectrum analyzer, not a signal analyzer, this is spectrum analyzer. Here we have the input signal, and to protect the remaining circuits of the spectrum analyzer, we have a variable attenuator at the input port of the spectrum analyzer, such that if the input power is high power, we are going to increase the attenuation here. So the input signal to the remaining parts of the circuits of the spectrum analyzer would be an acceptable level. This signal will be passed through a tunable band pass filter. This tuned band pass filter is based on something called dig, and dig is effectively some sort of ferrite materials. So by adjusting the magnetization or the DC biasing magnetization of the YIG filter, we can adjust the band pass of this filter. And effectively, the DC biasing magnetization can be adjusted by using a DC coil. And this DC coil is effectively fed by a tuning control circuit. This tuning control circuit controls two things. The input filter, the input band pass filter, and the voltage controlled oscillator inside the spectrum analyzer. And this tuning control circuit is fed by a sawtooth generator, such that by increasing the voltage of this sawtooth, we are going to increase the voltage of the voltage controlled oscillator here, and we are increasing the center frequency of the band pass filter of the YIG filter. So by this sawtooth, we are actually shifting the frequency from low frequency to high frequency. Now, if our signal at a certain moment lies inside the bandwidth of the YIG tuned filter, it will pass from the YIG tuned filter to the mixer. And then the voltage control oscillator will be on to the mixer. So the output, it would be the difference between the two frequencies and the summation of the two frequencies. By using a low pass filter, we can detect the difference between the two signals. So assume that I'm going to detect a frequency, for example, 1 gigahertz, and the VCO is 1.1 gigahertz. So the output here is 0.1 gigahertz or 100 megahertz. By using the low pass filter, I'm going to detect or to take the amplitude of the 100 megahertz, which is the combination of the mixing between the original signal and the VCO. This low pass filtered signal is fixed at a certain frequency. So the low pass filter here, or the remaining part of the circuit, are fixed at a specific frequency. So we are assuming that we are taking the difference between the input signal as a frequency and the VCO. So by changing the VCO frequency, we can sweep the different frequencies to see what is the components of the different frequencies at the input. Now, the output of the low pass filter is amplified by logarithmic IF amplifier, and the signal here now is detected by using a detector. Here is the rule of the detector. So the output of the detector, it would be a DC proportional to the amplitude of the signal, and the amplitude of the signal is effectively proportional to the amplitude of the input signal at the frequency of the VCO, such that the difference between the VCO and the input frequency is a fixed value, and as I said, which is IF of the spectrum analyzer. Now, the detected signal, it will have the amplitude proportional to the input signal. This would be very low frequency or nearly DC. This will be amplified by a video amplifier. This video amplifier will be applied in the vertical axis of the display. On the other hand, the sawtooth is used as the horizontal axis of the display. So the sawtooth is effectively sweeping along the horizontal axis as a function of, or representing the function of the frequency, and the vertical axis representing the amplitude of the input. So assume that we are starting from F1, F2, F3, F4 until F5, for example. At F1, if I have a signal with amplitude, then I have the amplitude of F1. F2, I have the amplitude of F2. F3, I have the amplitude of F3. F5, and so on. So I'm going to draw the amplitude of the frequency component of the input signal as a function of the horizontal scale, which represent the frequency in this case. This is the basic idea of the spectrum analyzer. And as I mentioned, the detector here, it can be a Schottky diode detector, as we mentioned in the previous video. So we say that a microwave spectrum analyzer can typically cover any frequency band in the range of several hundred megahertz to 10 of gigahertz. The frequency resolution is effectively set by the IF bandwidth of the low pass filter, and it is typically adjustable from 100 Hz to 1 megahertz. And it should be noted that if I have reduced the IF bandwidth, this means that I have reduced the background noise level. If I have increased the bandwidth of the IF, I have increased the noise level. A sweep generator is used to repeatedly scan the receiver over the desired frequency band. So we are going to adjust the VCO, the voltage controlled oscillator, by using the sawtooth to sweep along the required frequency band by adjusting the local oscillator frequency and provide the horizontal deflection of the display. An important part of the spectrum analyzer is the tuned filter, tuned band pass filter as the input of the mixer. This filter is tuned along the local oscillator, and effectively the tuning between the filter and the local oscillator will reduce the effect of the intermodulation or the spurious intermodulation product. So this acts as a pre-selector for the input signal to reduce the spurious intermodulation products. This briefly what is meant by the spectrum analyzer, and we have discussed this spectrum analyzer here as an extension part or as an application for the detector diodes, and we said that the detector diodes can be used as a Schottky diode. Okay. In the following video, we are going to discuss another type of microwave diodes, which is the B insulator N diode or Ben diode, which is mainly used as microwave switch, and we will see what is the application of such microwave switches. See you in the next video.